Okay, second video this evening. This Mog question 2, which I also put into the little question sheet I had last week. This is also a tough question. Both the questions I've gone through in this paper I think are quite tough, and I'm sure the rest are as well. I briefly glanced at the examiner's report, and just like on pretty much all of the extension papers and Olympiads and stuff, they're really transparent with the distribution of the marks. And yeah, this one was not, they did not, people found it very tough indeed. I'm not surprised. Okay, so anyway, number 12 may be factored into three positive integers in exactly 18 ways. Straight away I'm thinking, really? Where'd they get 18 from? Factors of 12 like this, what, three pairs? 1, 12, 2 and 6, 3 and 4? How are they getting 18? And then you see how they include these factorizations. Okay, so firstly, 1's allowed in it, so we're not talking about prime prime decompositions or anything like that. They're allowing for 1's, and look at this, 2, 2 and 3, and 2, 3 and 2. I mean, to me, they look like the same factoring, really, but clearly order is important as well, like counting the order. So that was the first thing I thought about this. I started thinking, well, can I get 18 just like, shaking it around like this? And I fully invite you to try it. I don't think it's worth spending time in this video now because it would just be involve us writing a load of lists, which we're going to be doing anyway in a second. But yeah, please, I fully invite you, see if you can get 18 out of that, just rearranging. It doesn't take too long, and yeah, you can certainly do it. So we're basically looking for pretty much every kind of shuffle we've got for all of the factors, including the number 1 and the number itself, because obviously, well, actually with 3 we couldn't really do it with just 1 and 12, but we could do 1 times 1 times 12, and we could do 1 times 12 times 1, and 12 times 1 times 1. There's a lot to think about here, there really is. Now, before we get started, there's a little bit of, annoying stuff for us. Let n be the number of seconds in a week. Okay, right, well, we've got to work out how many seconds there are in a week, I suppose. So, 60 times 60, that's the number of seconds in a minute, that's the number of minutes in an hour, times by 24, number of hours in a day, and times by 7, number of days in a week. Now, I didn't bother actually working this out because I realised straight away this is going to be about factors. So let's just think of this straight away in their prime factor decompositions. That's 15 times 4, isn't it? So that's 3 times 5 times 2 squared. Oh, but then we're timesing that by itself, so we're squaring that. And then we're timesing it by, what's that, 8 times 3, so 2 cubed times 3, and then timesing it by 7. And then it's to write it in a nice clear way. That's what's going to give us 2 to the 7 times by 3 squared, I think. Oh, no, 3 cubed, oops, times by 5 squared, times by 7. Okay, cool. So we need to see how many ways this can be factored according to their rules of factoring. Now, first look at the question. You're like, oh yeah, it looks difficult. This is clearly a counting question, as in like a permutations and combinations question, which I've never found particularly straightforward. You have to think carefully, you really have. They're good fun actually as well, and the more you do of them the better you get, without a doubt. This is something which can be practiced and you can get better and better at, but they're never easy, and you'll notice actually the maths challenges all the way down to junior maths challenge, you look at the harder questions from that, like they're always about these things, like they're good questions. Okay, so how did I start? I kind of thought first, let's point out that basically we've got 3 slots, yeah? So I drew 3 buckets. And I thought, in how many ways can I put let's just say just the 3's in, because then I can deal with the 2's and the 5's and the 7's, like, systematically afterwards. Because if you think about it, the 3's can all go in different orders here, yeah? Perhaps we could have, for example, all the 3's together, because we've got to use 3 of them. Now, if I don't write a 3 in here, that's standing for times 1, which I have to consider, don't I? So I could have 27, that means, times 1, times by 1, yeah? And that will make up for the factor of 27, which is within my number, yeah? Or I could put the 3's out in a different way, yeah? Let me just put them over here. I could maybe have a couple of 3's together, making a 9, and a separate 3 on its own, something like this, yeah? That represents naturally a factor of 3 times 9 times 1, yeah? Now, I haven't thought about how many ways these can be jumbled. I haven't thought about how many ways these can be jumbled yet. But I'm just kind of thinking, really, with the 3's, there's only a few things which can happen, which is all in separate ones as well, and this is just 3 times 3 times 3. Yeah. Now I haven't thought about bundling in the 2s and 5s and 7s yet, I know, but I'm just thinking about how many ways there are of ordering this, because this is a fairly standard ordering problem. Yeah. What we're really saying here, how many ways can you do that? Well, you think about it, you could put it there, or you could put it here, or you could put it here. That would represent the 27 times 1 times 1, the 1 times 27 times 1, and the 1 times 1 times 27. Yeah, which will be within the giant factoring when I've put all of my numbers, because remember, I'm going to have to use all of these numbers in these buckets eventually, so I've got some more difficult bits after this. But let's just count how many ways we can do this. Okay, that's 3 ways. Yeah. How many ways can you order that? Well, this is like an ABC problem, yeah, because they're all different and distinct. How many ways can you shuffle ABC? 6 ways, yeah, and you definitely want to get familiar with that kind of thing, because if in general, if there are n objects, then there will be n factorial ways of shuffling them, n distinct objects, I should say distinct. Think of like 8 different books on a shelf. In how many ways are there of ordering them? We've got 8 possibilities for the first slot, 7 for the second because you already used 1, 6 for the third, so it's going to be 8 factorial, 8 times 7 times 6. So this is just 3 factorial, which is 6. Okay, and how many ways are there shuffling that? Well, we've only got 1 way there, haven't we? Yeah, and so you can see there's 10 ways of doing that altogether. Yeah. Now, just remember that, because now we can think of like what we're going to do afterwards. Now, 3s are already in there. If you think about it, if we count all the different ways there are of shuffling the 2s in here, all we've got to do is times these to get all the different ways there are of shuffling both of them. That's like the product rule for counting, that is. If you're looking at, there's 10 different ways of organising the 3s, but then you're going to count how many ways there are of organising, say, the 2s, which will be more difficult, then all you're going to do at the end is just multiply things together once you've considered 3s and the 7. Okay, so let's do that. Okay, for 2, what do we got? Well, let's try and sort of speed up a bit. We've got putting all our 2s in here, yeah? So obviously there's once again 3 ways of doing that, yeah? We could have 6 2s and 1 on its own. Yeah, and this is the naive approach, by the way, but I'm going to show you the slow approach, and then I'll show you the really quick approach, which I didn't spot, I'll be honest, at the end. Okay, how many ways are there of doing this? Well, this is going to be, 2 to the 6 and a 2 and a nothing at all. Well, this is like an ABC problem, so 6. We'll have to do the 2 to the 5 and the 2 to the 2, yeah. Try and be systematic when you do these, otherwise it's easy to miss something. There's 6 ways of doing that. You've got and it doesn't take too long to list these out, but I did actually go through the tediousness of it. Okay, 2 to the 4 and 2 to the 3. Well, ABC, so it's a 6-1 problem again. And then we've got, don't forget, we can do things like 5 1 1. 2 to the 5, 2, 2. How many ways are there doing that? Well, this is like an ABB problem, so there's only 3 ways of doing that. And by ABB, I just mean like in this first one, how many ways are there of ordering? Yeah, I refer to them as ABB and ABC. There's 6 ways of shuffling ABC. There's only 3 ways of shuffling ABB. Once again, we've got 2 the same, so there's only 3 ways of doing that. That goes there, or in the middle, or there. Okay, right, keep counting. These counting problems, damn counting problems. 4 2 1, 2 to the 4, 2 to the 2, 2 to the 1. Okay, that's an ABC, so that's 6. And then 3 3 1, 2 to 3, 2 to 3 and 1. Okay, that is an ABB problem, so 3. And we've also got a 3, a 2 and a 2. And I think at that point I would have exhausted all possibilities. I hope so. That's an ABB, so that's also 3. Yeah. Satisfy yourself that there isn't any more we've missed. You might think, oh, shall I keep going low? Because if you notice, I've gradually been decreasing the biggest power. Oh, I messed up there. Actually, went back to 2 to the 5. I missed one because I think at first I was just considering all the ones where there was ones involved. I wanted to deal with those, and then basically I went to the ones where there wasn't a times 1 involved. Remember, an empty box means the times 1's there. Okay, so how many ways are there doing that? Let's add that up. 9 plus 12 is 21, 24, 36 ways. Okay, so my thinking here is I now can count all the different ways there are of shuffling the 3s. I can count all the different ways there are of shuffling the 2s. Yeah, I've just got to do the same with the 3s and the 7s. So let's do it. With the 3s, it's a bit quicker because it's only 3 to 3. Oh, sorry, it's yeah, I've already done the 3s. It's 5s. So I've only got 2 5s to consider. So 5 squared and 2 blanks, 6 ways. We've got for 3 ways for that, obviously. and a 5 and a blank. Yeah, and those are the only ways of doing it. Yeah, so there's going to be 6 ways in total there. And then you've just got the 7 on its own, the lonely 7. Well, how many ways are there of doing that? 7, 1, 0. There's only going to be 3. So at the end, what are we going to do knowing all these facts? Well, we're going to think, as I pack the boxes, which are really just the positions of the factors in the product, which clearly matter, annoyingly, because of that. I'm just now going to think, well, there's 10 ways in my first branch. Well, let's do freeze first then. 10 ways of doing the freeze. And then there's 36 ways of doing the 2s. And then there was, I think, 6 ways of doing the 5s and 3 ways of doing the 7. We now just multiply it all together. So what we got there, 360 times by 9. Well, that's going to be like, and have I done that right? 360 times by, I didn't see. Blimey, it's getting late, isn't it? That was an embarrassment. Okay, and so we're going to get 6480. Yeah, I must admit, I briefly glanced down at my notes there and realised, because I suddenly realised I'm sure the answer was about 6,000, and I'm getting with times 9, not 6,000. So, yeah, laugh at my mistakes. Okay, can I point out, though, there is a better way of doing this if you recognise the clever way of counting. They pointed this out in the mark scheme, and if anybody is reading it and puzzling, like they had a really clever way of doing the boxes. What they thought of it as was, like, let's say you've got 7 2s. And you want to count all the ways there are of doing the 2s. You can think of 2 parallel lines, yeah? That would notate basically all the 2s being in the last box, nothing being in the first box, nothing being in the second box, yeah? And then how many ways are there of ordering these lines? Because every single one counts the number of ways of how many ways there are of putting the 2s in the box, if you see what I mean. Every single different way there is of putting those parallel lines in. How many more have we got, say, yeah? So this will represent another possibility. Well, if you're deciding how many ways there are of positioning 2 objects in 9 positions, yeah, that's a 9 choose 2 problem. Yeah, and if you've ever heard how n choose r is used, but particularly n choose 2, like well, and n choose 3. If you've ever done any proper permutations and combinations, you'll know that you just can handle that straight away with 9 choose 2, and 9 choose 2 is 36. Yeah, let's do a similar thing with the freeze. Was it? I think the freeze there were. How many 3s were there? 3 cubed. Yeah. So we've got 3, a 3, and a 3, and we're trying to put these lines in one of 1, 2, 3, 4. There's there's basically 5 positions because there's 2 lines to put in, and that basically is a dividing line making the 3 boxes. It's ever such a clever method. It really is. When I read it, I thought that is crafty. I wouldn't have spotted that. Can you see there's this position, this position, this position, this position, this position? There's actually 5 positions there. So how are we going to work it out? We're just going to do 5 choose 2, which is 10. Very crafty, it really is. Do you see what I mean by these parallel lines? They're representing the middle bits of the boxes, and so they can divide it up into the left, the middle, and the right perfectly. Ever such a clever way of doing it. You get exactly the same things for the 5s, where you've got 5. There's basically 4 positions for them, so it's just 4 choose 2, which was 6. And it's the same with 7. Basically, how many ways of ordering that? Well, you've just got 3 choose 1, which is 3. Yeah, and then you can just times it all together at the end. That's a really crafty way of doing it. I didn't see that. I actually went through the whole process, but there we go. Okay, I hope you found it useful anyway, or gave you a few ideas. If you want to ask me about the N choose R stuff, definitely please do ask me at work. I'm very interested in explaining what little I can of it. Bye bye.